So today we're going to look at the Crank-Nicholson finite difference equations of a beam insulated bar. Lo mismo. So here we have our insulated bar. I'll draw it up here. And our insulated bar is 50 meters long. And overall, the bar is 20 degrees Celsius. We'll write that down later. However, on this side, right here, it is 50 degrees Celsius. That is a constant. That is on our left-hand side. So if we had like little segments. So from here over, this is all 20 degrees. And then on this side, we have insulation. And so we're going to be analyzing the temperature of the bar over time and throughout the bar. So we know that our boundary conditions, I'm just going to write them right here. T of x equals 50 meters equals 50 degrees Celsius. Joking, I'm gonna have this as 0 meters. And this temperature, x equals 50 meters equals 20 degrees Celsius. And so our change in x is gonna be 1 meter. Our change in time is gonna be 1 second. So this is important because our change in position for when we graph, that means is 1 meter. So that means we're gonna have 50 different segments of our bar. And so it's important to look at the change in time because obviously as time continues, the temperature will change. And we're looking at over an hour, which is 3,600 seconds. And so we'll be graphing it every 5 minutes, but we'll get to that later. Alrighty. Now that we have that, so we're going to look at linear diffusion we're going to use a partial derivative because obviously temperature changes with respect to time and position since we have two different temperatures on each side of the bar. So our partial derivative, our change in temperature due to our change in time is equal to alpha, which is our thermal diffusivity coefficient, which I'll explain in a hot second, and then times our change in time or temperature over our change in position squared, which is wherever we are in our segment. So our thermal diffusivity coefficient is a material property, and it's given in the problem as alpha equals 1 meter squared over second, and the thermal conductivity, it's a thermal conductivity divided by the density and specific heat capacity at a constant pressure. I looked that up on the internet, but that's sort of like the mathematical, but it measures the rate of transfer of heat from a material from the hot end to the cold end. So it's just how our heat is going to transfer through the material from the 50 degrees Celsius side to the 20 degrees Celsius side. And so now we need to sort of write this equation numerically because, we need to look to see how it changes throughout time. So we're going to use a Taylor series. Well, we'll get to the Taylor series in a sec. But if we have our temperature based on position and time, so J is going to represent our delta X, our position, and N is our change in time, or delta T. That is equal to our TJ plus 1 minus. So the way that we're looking at this is our change in time. So basically, the way we're going to look at this is looking at the time succeeding, the temperature succeeding our original temperature. So this right here is our temperature difference of the same segment at a different time. This is not equal to. This is equal to. And so this is going to equal, so this is taking this equation right here and just rewriting it. So our alpha times our t. So now we're going to change our position. So the segment before minus the segment we're on plus the segment after over our change in position. And so this is just a temperature difference of 3 different segments. So the segment we're looking at and the segment next to it at the same time. And this is, you know, looking at the same segment at different times because we're comparing our temperature based off of our change in time. So now that we have these equations, we want to sort of collect our coefficients together. So our coefficients are going to be change in time, alpha, and our change in x, because those are all given. So we're going to combine those to make our coefficient r. So we're going to move our change in time over. So we have our change n plus 1 minus position n equals alpha times our change in time over, oopsies, our change in position squared, and then times our temperatures. Oops, I forgot the t. Okay, so this is what we're going to use, oopsies, for r. So now we're going to use a system of linear equations, and it's going to be like a Taylor series where the temperature that we're looking at, n plus 1, depends on the temperature or on the time or position preceding, or n. And then since we have our initial temperature, we can solve for the succeeding temps. And I'll kind of explain what that means. So what that kind of means is when we look at our initial temperature, T equals 0, our 0 segment, it's going to be 50 degrees Celsius, which we'll handle that in our matrix. So this can get kind of messy algebraically, which is why Crank and Nicholson were like, hold our drink, we'll take care of it. And so we get the algebraic equation. That was just the speaker. Negative r j minus 1 to the n plus 1 plus 1 plus 2r temperature at j at time n plus 1 minus r temperature at j plus 1 at time plus 1 equal to r j at j minus 1 at n plus 1 plus 2r. Oops, that's a minus. T to the j n plus r t j plus at j plus 1 and n. So we know r is, that's our coefficient, and r equals alpha times change in time 2 times del x squared, and that 2 is just from the algebra above. Crankin did that. And so we know our coefficients, we don't really know our temperatures, but once we start plugging in temperatures, they'll give us once we plug our input temperatures, we'll get our output temperatures. So we're going to look at matrices to solve these problems, because there's obviously a lot of variables going on. So we can use the equation for a matrix as A times X equal B. So this side this whole side right here is B. And we know that from A and X, and A is going to be our R, or our coefficients, and X is going to be our temperatures. And so J equals 0. J are our positions. We're going to look at the positions of our segments, ... to look at our matrices. So this is going to be at J equals 0 is going to be our left boundary, and at J equals 49, which is 50 segments, is going to be our left boundary. And so those two are going to be kind of different than our main equation that we have above right here. But, so we're going to not quite do, oh wait, here, we'll do j equals 49. Do j equals 0 because that one's unique, and so we'll end up coming back to that. But basically j equals 1, you know, we're going to have our coefficients, negative r, 1 plus 2r, negative r, and then dot, 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 you know. As a Taylor series, it continues. And these are just going to be zeros, so we don't worry about them. And then our t would just be, you know, we're looking at t, j, it's the n plus 1. So we could look at t to the 1 time n plus 1. And so we would just use this equation right here. So this is b, so we would just use b. However, so if we look at our bar at j equals 0 right here, so this is j, we already know the temperature. They told us the temperature. It's 50 degrees Celsius all the time. So we look at the segment to the right, and the temperature is known at t, the temperature at j minus 1, and so we move it to the right side of our unknowns, which sounds kind of confusing. But basically what we're going to do is we're going to take this, because we already know what, so this is this temperature right here, 50 degrees Celsius. So we already know that. So we're just going to move it to our sides of knowns when we look at the segment that's directly to the right of it. So at j equals 0, we already know temperature is 50 degrees. You know, it's given. It's going to be 1 plus 2r, temperature at j, n plus 1, minus r, t, j plus 1, n plus 1 equals r, t, j minus 1 to the n, plus 1 minus 2r, t at j at n, plus r, t, j plus 1, n. And then we're going to add plus r, temperature at j minus 1, n plus 1. Because we already know this is going to be our 50 degrees Celsius. It's a given. And so this right here, I will call this BR, would just go right here for at j equals 0. Because it's already known. Okay? So that's the right boundary. So now we have to look at the left boundary. Or no, I think I mixed my lefts and my rights. Gosh darn. So this is actually on the left side. I confused my lefts and my rights, but it happens. So this is going to be BL. Let me just make sure. So that sometimes happens. That's our left boundary. Now we're going to move on to our right boundary. So our right boundary is perfectly insulated. And when we mean perfectly insulated, we're assuming that there is no heat transfer. And so when we assume no, okay, let me write, this is left. This is gonna be right. When we assume no heat transfer, that means what I'm gonna say is that our temperature at J is going to be equal to our temperature at J plus 1. And so our temperature at J is the temperature of our last segment equal to, like, this last segment right here. Because this heat right here is not leaving. So is going to be equal to the temperature. I'm going to say the segment at the insulator. I'll call it the insulator segment, or just the insulator. Okay. So that means we can sort of simplify our above equation. So let me rewrite out that equation. Temperature at J minus 1, n plus 1, plus 1 plus 2r temperature at J, n plus 1, minus r temperature at J plus 1. And so remember, this side is looking at our position, the change in position of our segments. Oh, pardon. Yeah. Equals. Oh, did I write this down correctly? 1 second. Yeah. And then the temperature. Oopsies. And then this is R, temperature. Oh, this was looking at our change in temperature, pardon. Or no, yeah. R plus 1, n plus 1, plus 1 minus 2r times temperature at J. And, oh, I wrote this down wrong. This is just n. Oh, this was the Crank-Nicholson combination, JK. Plus r temperature at J plus 1 n. Okay. So, if temperature at J is the same at the temperature of J plus 1, that means these two and these two are equal to each other, and these two and these two are equal to each other. So we can simplify of 1 plus 2r minus r equals 1 plus r. And this will simplify to 1 minus 2r plus r equals 1 minus r. And so our equation on our right boundary is negative r temperature at J. It's 1 n plus 1 plus 1 plus r times the temperature we'll call it J at n. And then this is going to equal r times t at J plus 1 at n plus 1 minus r at temperature of J at n. Okay, so this is going to be our right boundary, which would go all the way at the end, boundary of our right, and we're going to have our just regular Crank-Nicholson equation. And so now we have, you know, looking at our left and right boundaries, which are different due to the conditions, and then also looking at throughout our bar. So now that we have these equations, we are going to put them in code to graph them to look at the change in temperature due to position and time.